All right, folks. Oh, got to get out of this costume soon, but we'll get started on the writing here. All right, this is the last lesson that is going to be on the test on Monday. It's called the common ion effect, and this is an effect on the solubility of a substance due to the presence of other ions in a solution. At the very beginning of this little section on solubility, we did our general equations to determine the solubility of various salts, Mx, Mx2 or M2X, Mx3, etc., etc. And we said that the solubility was the X value, right, in our equation. And we came up with a handful of equations to determine the molar solubility of that substance. How many moles per liter of that substance will dissolve and break apart into their ions? And we did some calculations where we calculated for X. Now, back when I did those problems and I was building the ice table, I indicated to you that these questions were being done in pure water. In other words, the ions that were there at the beginning in the initial conditions were 0 and 0. There was nothing there. It hadn't dissolved. And therefore, we then concluded to get X and X and X and X. And then if it's an MX, we got X squared, right? And the X was the square root of KSP or something like that, right? And that all those problems, I wanted to stress to you, and I did want, that they were done in pure water. The common ion effect is exactly the same question, determine the molar solubility, how well something will dissolve, but it's not in pure water. It's in water that already contains one of the ions that we're worried about, one of the ions that are in our ice table. What this means is when we build our ice table, my initial ion concentrations will not necessarily be 0. There will be something in there. It's as if we're starting with some of the product already. We know how to solve these problems. We know how to deal with an ice table that has something other than 0 in the I line. So this is not a new problem. This is really more of just an application of solubility that has this effect that when you have a common ion, the solubility of the substance changes. And that's what we want to look at. Okay, I'm going to bring the whole thing up, and you can write it down. This is worth writing down, and it also gives me an opportunity to get out of this crazy costume. Okay. So we're going to be talking still about our ionic solids that have very low solubility, very small values for K. we're really not worried about doing problems on solubility in terms of solubility equilibrium when we deal with something that's very soluble. So we're still dealing with these salts of low solubility. For example, lead-2 iodide, breaking into lead-2 and then iodide, obviously, 2 iodide ions. But instead of us dealing with pure water where in our I line we had 0 and 0, what if we were trying to dissolve that particular substance in a solution that already had sodium iodide dissolved in it? Now, sodium iodide is very soluble. It's sodium. It's part of that that group that I had to try to memorize last year from that silly song, right? Potassium, sodium, ammonium salts, whatever they may be, can always be dependent on for solubility, right? Remember, that's with the spectator ions. Did I not sing you the solubility song? Oh, you've not heard it? I'm not going to sing it. Because you can just listen to the words. No, I'm not doing it. Potassium, sodium, ammonium, salts, whatever they may be, can always be dependent on for solubility. No, that's not singing. That's just rapping. I rapped it. I'm much cooler than just singing. Anyway, those are our spectator ions. So sodium iodide is going to be very soluble. The K will be very large. We don't even bother solving the problem using an equilibrium situation. So when this dissolves, we get Na plus aqueous and we get I minus aqueous. And a question would go, determine the solubility of of lead-2 iodide in a solution that already contains sodium iodide. So essentially, we need to identify which is the common ion between these two salts. I'm hoping it's really obvious. The one in common iodide. Yeah, it's iodide. I said iodide instead of ion. Gave it away. It's the iodide ion. What this means is, in our ice table, we're not going to have zeros anymore. In other words, we can't use all of our nice little shortcut equations that we derived, right? We derived all these great shortcut equations for when the solution was pure water. Well, it wasn't a solution then, when it was pure water. So now we actually have to go through an entire ice table, but it's not a difficult thing. So if I've got extra iodide on the right, to begin with, this causes the equilibrium to shift left. We can think of it as a Le Chatelier situation. And if it shifts left, it means we're going to have less of it dissolved, and it means the solubility of the salt, the very low soluble salt, in this case lead-2 iodide, is reduced. So when you have a common ion, the solubility of that particular substance that you're studying will be reduced. And that's what is technically known as the common ion effect, a reduction in the solubility due to the presence of another salt that has a common ion. Now, I handed out some sheets yesterday that had the practice problems on them, and therefore you don't need to write these practice problems down. And if you were not here, you may want a copy of that sheet. And I also have a sheet for later on that has some practice problems on it other than textbook problems, but I'll hand that out later. So I've also got another sheet here. So if you weren't here and you don't want to copy those questions, or if you don't want to copy them and you want to grab this later on, it's right there. So we are doing the bottom part of the page right now, the common ion effect problems. Okay? All right, let's do our example problems, be done, and then you guys can work away. So this is the one at the bottom. This is number 1, determine the solubility of lead-2 chloride in pure water in 0.2 moles of lead-2 nitrate or in 0.05 moles of calcium chloride. We are going to need the KSP for lead 2 chloride on this. I will again give this to you. I will give this to you on the test, like I said. This is what, page 7. There we go. What do we want? Lead 2 chloride. Lead 2 chloride. If someone could write this down for a moment, 1.2 times 10 to the minus 5 is the KSP. We need that. 1.2 times 10 to the minus 5 is the KSP. So 1.2 times 10 to the minus 5. I suppose I could write it down. Okay, where's something to write with here? This will do. So KSP 1.2 times 10 to the minus 5. All right. If we're talking about lead chloride, PbCl2, solid, and that's going to become Pb, and I'm messing this up already, Pb plus 2 plus 2Cl minus. All right. Now I'm going to clear the screen as I go through these just because I need some space to do all of them. If it's in pure water, then we can do this problem using our shortcut if you've memorized your equations. If you haven't memorized your equations, you can still build the ice table 0, 0, right? X and 2x, because this is an mx2. And in the end, we want the molar solubility. So in the end, I'm looking for x. So you can go through the entire equation if you'd like, or if you remember what that shortcut was, you've memorized that for your test. In pure water, you can use the equation. You can use the shortcut. I'm going to just keep going here. Obviously, x2x, x2x. Right? It doesn't take much to do it from beginning, but if you had it memorized, you could go right to that end. You'll notice that when I ask this question, this is likely going to be out of 2 marks. Put your equation and, give me the thing. But if you want to write out an ice table, that's fine. It really doesn't take that long. Therefore, the KSP is equal to x 2x squared 4x cubed. And if you recall your equation, x is equal to the cubed root. This is kind of like a little review here. I got to bring the 4 underneath there. I think it's KSP over 4, right? And that was our M2X shortcut equation. If you had it memorized, great. If you didn't, you can run through it and quickly get it. But if it's in pure water, then we've already done that. That was our first day on molar solubility. Cubed root 1.2 times 10 to the minus 5 over 4. And again, you've got to do the 1.2 times 10 to the minus 5. You've got to divide it by 4, then cube root that answer. Yeah, Ben, what do you got? 10 to the negative, 2? 10 to the negative 2. Because we're doing a molar solubility, I do need the units, moles per liter. Are you okay with those numbers? It's good? So, in pure water, that's what we did on that first day when we talked about things dissolving. Might have been even Monday, I think it was. All right? Now, the next one, in 0.2 moles per liter of lead 2 nitrate. So I'll clear the ink. Again, this time I have to put the ice table. So PbCl2 solid, Pb plus 2 aqueous plus 2Cl minus. Now, if I have 0.2 moles of lead 2 nitrate, well, number one, what's the common ion in the lead 2 nitrate? What's the common ion? Lead. So from that, I can determine the concentration of lead that's already in the solution. I'm just going to put this up here just because I don't have a lot of space. You might have some space to the right of your page. Concentration of Pb plus 2, that's already in there at the beginning. Well, there's 0.20 moles per liter of lead 2 nitrate and there's one lead. Well, I should maybe write down the formula, right, so that we can see it. That's, well, I'm going to write it down in a second, right? It's lead 2 nitrate, so there's one lead to 2 nitrates from the crossover, 1 Pb plus 2 per 1 PbNO3 brackets 2. That's that classic conversion factor that tells you how many ions are in each thing. So all I'm doing is I'm plucking out the number of the amount of ions in that lead nitrate. And because it's 1, it means there's 0.20 moles per liter of lead ions. Which means when I do the ice table, I don't put the solids in. I now have 0.20 and 0. In other words, it's not pure water. There is a common ion in that solution. But I solve it now exactly the same way as I did before. I use all the techniques that I've used before. If I can take a perfect square, that's excellent. If I can use the approximation, that's great. If I can't, I might have to use a quadratic equation. It depends on what happens through here. All right, so let's keep going. So this is going to be x and 2x still, 0.20 plus x and 2x. Put it into the expression. What was that number? 1.2 times 10 to the minus 5. Is that what that was? And that is going to be equals 0.20 plus x, and this is going to be 2x all squared. And now I slow down for a second. I need everything to be squared in order to take a square root. And this factor here is not squared, so I can't take a square root. I don't have a perfect square. If I FOIL everything through, I'm going to have some x cubes. And I don't know how to solve an x cube. I haven't taken that type of math in a long time, so I'm not going to go there either. So next, I have to check for the approximation. So let's do a quick check for the approximation. What number am I dividing over the KSP to determine whether the approximation is good? Little approximation rule here. Shauna? Yeah, that number that I'm going to do the plus or minus from, that initial concentration, 0.20 divided by the KSP, 1.2 times 10 to the minus 5. And again, I just need an approximate number there. I just need to know if it's bigger than 100 or not. What do you got there, Jess? 16,000. So 16,000 is indeed greater than 100. Therefore, the approximation is good. And again, just to remind ourselves, which x am I able to get rid of validly? Yeah, Elena? Yeah, the one that I'm adding to the 0.2, because it's really tiny, right? So that is essentially 0. It's approximately 0. Maybe we should put a little approximate sign. It's not a big deal. So now I rewrite and I solve for x. 1.2 times 10 to the minus 5. Now that's simply a 0.20, but that's still a 2x squared. So I'm still going to get a 4. Then I got to divide those two numbers off. 1.2 times 10 to the minus 5. Many ways of approaching this at this point. And then that's going to be times 4x squared. So you could combine those two numbers, or you could just divide off a 0.2 and divide off a 4, right? However you want to do that. I'll bring it into this space here. So if I 1.2 times 10 to the minus 5, divide off the 0.20, divide off the 4, that's x squared. Now I can take my square root. X equals. And again, that x is the amount of this solid that was able to dissolve, even though I started with 0.2 mole lead ions. It's still the molar solubility, but it's now in a solution that isn't pure. What do we have for a number? We got a number? What do you got there? Number? 3.87 times 10 to the negative 3 moles per liter. We should be rounding probably to 2 significant digits along the way, but I'm not worried about that right now. You guys are good at that during the test. What was the previous answer? What was it in pure water? I can't remember. I cleared the screen. 1.4 times 10 to the negative 2, right? And now the solubility is 3.87 times 10 to the negative 3. The solubility decreased. Not as much could be dissolved due to the presence of those lead ions. Because when they start to dissolve, the lead ion number is going to be bigger, and you're going to get to the value of the KSP sooner, and therefore a precipitate would start to form sooner because there's more of that other stuff in there. And therefore it shifts left, and we say that the solubility decreases. Let's do the last one here, calcium chloride. The only reason I'm doing this one, clear the ink, has everything to do with the formula of calcium chloride. That's the only reason I'm doing this. You guys are pretty good at getting the idea of things done, and I know you get frustrated when I do too many examples that are the same. But the only reason I'm doing this is because, well, if I've got lead 2 chloride, PbCl2, solid, and Pb plus 2, I'm doing the same stuff, Cl minus, and that's 2 of them. What's the common ion in my calcium chloride? The chloride, right? That's pretty straightforward. And here's the trick to this one. But you know what? You'd be surprised. I've had classes in the past that blow this completely, out of the water here. Calcium chloride, if I have 0.050 moles per liter of CaCl2, the question is, what's the chloride ion concentration in that thing? What do I have to do with that number to get the chloride ion concentration? Yep, Kristen? Multiply it by 2. Ooh, that's the Halloween theme right there. Scary question. Not really. Because there's 2, the chloride ion concentration is 0.050 moles per liter, and the ratio here is 2 chlorides per 1 calcium chloride. Oops, that's 2, not a negative. So what I'm saying is, be aware of that common ion, whatever the formula is. If you've got to double it, you have to double it. 0.100 moles per liter. And actually, I can't add a significant digit. Can't do that magic there. So again, in this case, it's 0 and 0.10. So we had to double it because there's 2 chlorides in each calcium chloride. Now we fly through the problem the same way. X, 2x, x, 0.10 plus 2x. 1.2 times 10 to the minus 5. This is an x, and this is 0.10 plus 2x all squared. Actually, there's some other useful things that you got to watch for in a problem like this. Again, I'm going to end up with x cubed, so I've got to check for the approximation. Again, the approximation check in this case is going to be the 0.10 over the 1.2 times 10 to the minus 5, and it's half the value. Instead of what we have, 13,000 or something, we're going to have 7,000. You could run through the calculation, but for the sake of speed, I know, and you should know, hopefully, that that's going to be greater than 100. I've got a 10 to the minus 5 in the bottom, and I got a 10 to the minus 1 in the top, and if I do a power of 10 estimation, the minus 1 gets rid of one of those, so I've got a 10 to the minus 4 in the bottom. When I flip it to the top, it makes it become 10 to the 4. That thing's going to have 4 zeros on the end of it. Much greater than 100. So, approximation is good. What am I getting rid of here? Which of the x's am I getting rid of? Shauna? Yeah, the 2x. Because again, this is the big number that I'm adding that x to, and even though it's double x, x is tiny. When you multiply a tiny number by 2, you just get 2 times the size of a tiny number. You know, if you multiply it by like many powers of 10, you start to make it big. But just because you're multiplying by 2, no effect. So this is the guy that then is approximately equal to 0. And I guess then there's one more pitfall I can warn you about in this problem. 1.2 times 10 to the minus 5. And now I've got an x there. And in this bracket, I've got 0.10. And here's where a common little mistake happens during a test because you're flying. You've just determined you're going to drop this off, but we also forget that there's still a square on the back end of that thing. I still have to square that number, all right? And that's where many little mistakes take place, right? On the test, that's still a -1, but hey, -1 is -1, right? So dividing that off, x is equal to 1.2 times 10 to the minus 5 divided by 0.10 all squared. And I'll take it when you got it. Ben? 1.2 times 10 to the negative 3. Again, moles per liter. It's a solubility. And again, that first one was -2. This is -3. Again, the solubility has decreased due to the presence of the common ion. Okay? So there are the basics of the common ion effect. I think I've got 2 more examples, so we'll plow through them. Let me know if there's anything that isn't making sense. I figure the faster I can plow through it, the sooner you can get to doing some practice problems so that you can free up a little bit of time for your trick-or-treating tonight. All right, because trust me, when I told the grade 11s we were having a test tomorrow, there was a trick-or-treat wine fest going on. And I said, really? Man, I don't think so. And then they said, you should bring candies for us. And I said, find a grade 8 teacher who cares. I know, but I thought it was funny. Even had a parent at the arena. Did you know so-and-so? She's very upset that you have a test. Really? That's good to know. I can use that information. Okay, determine the maximum concentration of fluoride ions that can be dissolved in 0.020 solution of magnesium chloride before a precipitate of magnesium fluoride ions forms. You need a KSP for this. And again, I'm going to give you all that stuff. So there will no, you won't have to go looking for it. And the precipitate is magnesium fluoride, so that's the one I need. Magnesium fluoride, 6.4 times 10 to the minus 9. 6.4 times 10 to the minus 9. Now, in questions like this, it can be a little complicated on what we're actually looking for. This one's not too bad, but you see, if we don't truly understand what's going on, we sometimes think, oh, it's magnesium chloride that we're dealing with, but we're looking to form a precipitate of magnesium fluoride, which means MgF, and I got to cross that over 2, is the substance that I am interested in concerning my equilibrium. Concentration of fluoride ions simply means I'm looking for the equilibrium concentration of the fluoride. I want to know how much fluoride can be in there. Now, even though this doesn't say solve the solubility of magnesium fluoride, that's exactly what we're doing. So, what's the common ion in my magnesium chloride? Magnesium. That's the easiest question you got. So, magnesium chloride is MgCl2. So that's a 1-to-1 ratio. And therefore, what's my initial concentration of my Mg? I'm trying to do this a little quicker. I don't need to write out that conversion factor each time. You guys are hopefully starting to see that. If I've got MgCl2 and I've got 0.02 molar of magnesium chloride, how much magnesium is going to be in there? What's the concentration of the magnesium? Yeah, it's exactly the same. It's 0.02. 0.020 moles per liter, all right? So you don't have to write it out as officially each time. I'm just trying to, show you where it's coming from. Ice and 0.020, and this is 0, right? And then I'm going through the ice table exactly the same way. This is going to be x to x, 0.020 plus x and 2x. And in the end, it's asking for the fluoride ion concentrations. There it is there. It's 2x. All right? So we're looking for the solubility, and then we're putting it back into that. Remember when we were doing equilibrium calculations, we would put it back into the equation? That's all we're doing here. So it's just an extra little step. 6.4 times 10 to the minus 9, 0.020 plus x, 2x squared. Again, I'm going to have a cube. 0.020 divided by 6.4 times 10 to the minus 9. Look at that, 10 to the minus 9 on the bottom. I flip that to the top, what does it become? It becomes 10 to the 9, right? So I got a 10 to the 9 up here along with a 10 to the minus 2. That's a 10 to the 7, which means we're talking about millions for that calculation. It's okay to calculate it out, but if you're doing it, you're going to find that this is much greater than 100, hugely greater than 100. Again, the approximation is good. Can't get rid of that x or everything becomes 0. So that x is approximately equal to 0. And I'm going to just speed this up a little bit. We're going to have our number. Going to divide off the 0.02. There's no squared here. And I'm going to divide off a 4, right? 6.4 times 10 to the minus 9 divided by 0.020, and then divided by the 4, and that leaves me an x squared, and therefore, in the end, x is equal to. You guys are a bright bunch. You fly through it pretty quickly. What do you got? 2.8 times 10 to the negative 4, and that is x, which is the molar solubility. But this question asks fluoride ion concentration. So I need a 2x, 2 times 2.8 times 10 to the minus 4, and what, 5.6? 5.6 times 10 to the minus 4 moles per liter. Really the same question. Again, this kind of reminds us of the fact that we're really talking about equilibrium problems here. First lesson I did when we did solubility in pure water, I quickly ran through these shortcuts. And you kind of got, this is good, this is fun, I like the shortcuts. But we soon forget that we're dealing with just a regular equilibrium situation. Here, with the common ion, I have to do the ice table, and I run through it the same way, the same logic. So instead of asking me for the solubility, it's just asking me for the fluoride concentration. I just need to do an ice table and then find what that fluoride concentration is. And I got one more, and you'd think it was very repetitive, but again, the reason I do it is because it's a little twist on the previous question. Oh, rat. Oh, no, we're good. I got to set up my nitrogen triiodide explosion over there, and I got to pour that soon. But I'll be done soon. I'll be able to do that. Just like any of our other equilibrium problems, every once in a while they stick in a problem where it asks, oh, what's the KSP? That just means we have to fill out the ice table, get all the numbers in the E line, and then just dump it into the equilibrium expression law. And so that's the plan of action that we're going to use. And that's true anytime it asks to determine a KSP, right? Even though I've wrote all these different rules down way back when, and it was saying, calculating K If you're given the E's, you just write it down. But if you're given some I's and just one E and need an ice table, you get all the E's and away you go. That's what we're dealing with here. We at some point got to find all the E's. Then we can just put it in the expression and do that. It was found that the molar solubility of strontium fluoride was that in 0.5 moles per liter solution of calcium fluoride. So still the molar solubility is this particular variable in all of our equations, and that's a true statement still. What is it that we're given here? When it says the molar solubility is, and that's the number we're given, what is that in our equations? No change. What do you got, Kristen? X. Molar solubility is X. So in other words, they've given us the X. Because it's in a solution that contains a common ion, it simply means I don't have zeros all the way across the top. So I put in what I know on the top. I put in my X's. I've been given X. I dump it in. I now have all the E's. I stick it in and I find the KSP. Again, the tricky thing is, which one do I use? Strontium fluoride or calcium fluoride? I need strontium fluoride. And that's because that's the molar solubility they've given us. So if they've given us the molar solubility for strontium fluoride, that's the one I want to find. And it says it right there. So what is that? SRF2, strontium in group 2. I just put the periodic table up. Is it 2? Group 2? Yeah, group 2. Strontium fluoride, and that is solid strontium plus 2, F minus, and that's a 2, ICE, solids don't appear. Calcium fluoride, CaF2. What's my initial concentration of the fluoride ion? I don't want to calculate it. I don't even necessarily need to see you calculate it, unless it's the only thing. Yep. 0.1. 0.10. That's because there's 2 fluorides in each calcium fluoride, so I've got to double that number, right? That's the 2-to-1 ratio. I can write it out if you'd like. And like I've always said, you guys are pretty quick, so, calcium fluoride, I got 2 fluorides. There's my concentration of calcium fluoride. It's got to double that number. And this is 0, and this is X, and this is 2X, and this is X, and this is 0.10 plus 2X. And if you want to put the X in there now, you can. But what I would do is I'd probably just keep going, and I'd just go KSP equals, because we've been doing this quite a bit. This is going to be X times 0.10 plus 2X all squared. And now I'd sub in the number for X and I'd calculate it. Because they've given us the molar solubility. X is equal to 4.3 times 10 to the minus 7. And so 4.3 times 10 to the minus 7, 0.10 plus 2 times 4.3. Times 10 to the minus, oops, that's a 7, 7, and that's all squared. Take a look here for a moment. You can keep calculating, but look at 4.3 times 10 to the minus 7 plus 0.1. What's that answer going to be to 2 significant digits? 0.1, without even calculating it, plus 2 times 4.3 times 10 to the minus 7. Yep. It's going to be essentially 0.1. 10 to the minus 7 is way out there in significant digits. It's way off there in tiny little decimal land, right? Wherever that is. Be a nice place to visit maybe someday. But anyway, it's way out there, and therefore, really, this is going to be equal to 0.1. That's why we could use an approximation in this situation. So if you wanted to save a little time, you could probably just do 0.1 squared times that, and you'd get the same answer. But you all crashed through, which is great. Nothing wrong with that. What do you got for a number? Yep. Yeah. 4.3 was it? I didn't catch it. Yep. Times 10 to the negative 8. -8. She said with a little question mark at the end. We got supporters. We like it? All right. Excellent. Good job. And that's my last example, I believe. Oh, -9? All right. You didn't have the calculator do it, so you counted back. That's okay. We're good with that? Okay. There are, wait a minute. Yeah, there are the questions out of the textbook. I'm going to give you some extra problems here just because, the more you do, the better, the more practice you have available, the better you get at it. Again, ignore the text questions on this sheet. I haven't updated this sheet for the new textbook yet. And on the next slide, I also have test review problems. And this new textbook has piles of them. Don't feel you have to do every one of them. Some of you feel you have to do every one of them. Some of you don't, but that's okay. So there's some practice problems. And yeah, it does say 1 to 59. I haven't even picked out some of the, I was going to send Jenna right over the defense. Maybe I shouldn't hand out this extra page. Oh, that's good stuff. This new textbook, I must admit, is much better at supplying text questions, which means I can actually start phasing out some of these old handouts that I had because the textbook now has more questions. What's that? Well, there you go. You got plenty of time now. You could probably go trick-or-treating tonight. What? That was cool. It just jumped right out of my hand. Like a ghost. Threw it out of my hand or something. All right, here, you can keep that one. Well, you guys are getting good at studying and knowing what to do and what not to do. You're welcome. Hey, you know what? I even have common ion questions at the bottom of that sheet, don't I? And is it the same questions? I shouldn't have photocopied this. No, they are different, but you know what? I apologize. You guys have way too many problems here. But what I've done is I gave you that big long sheet, and then I forgot I don't need to make this sheet anymore because I've got those on the bottom of the sheet. Do enough of them until you feel confident, right? You guys, yeah, you guys are good. You feel confident. Okay.